Hello everybody to my talk, Tiny Machine Learning Virtualization for the Internet of Things and Edge Computing using the REXA virtual machine. My name is Stefan Bosse. I'm a researcher and lecturer at the University of Bremen and the University of Siegen in the departments of Mathematics and Computer Science and Mechanical Engineering. And today I want to give an introduction or an overview of a very challenging job to implement machine learning on low resource microcontrollers, for example in sensor nodes in computer and sensor networks. I have a short overview. Tiny machine learning is a new approach that is being used for data-driven prediction, classification and regression on microcontrollers using local sensor data. But even simple sensor data acquisition, aggregation and processing is a challenge in distributed sensor network environments like the Internet of Things, mobile networks, mobile ad hoc networks and other distributed, strongly heterogeneous networks. The goal of this work and the REXA virtual machine is to process sensor data locally and derive compressed relevant information features like damages, attack features in a network environment and so on with final global feature fusion. I give a short overview and about the virtual machine and the challenges, and to overcome issues and limitations with software and machine learning deployment and strong heterogeneous computer networks, the real-time, capable, low-resource virtual machine REXA VM is introduced. So, REXA VM provides virtualization of basic machine learning operations and models, including, but not limited to, decision trees, artificial neural networks, convolutional neural networks. The REXA VM and its ML operations can be deployed on very low-resource microcontrollers like the STM32 ARM Cortex series, starting with 20 kilobytes of RAM only. So here, let's start with an example from my colleagues from the University of Bremen and the IMSAs, Björn Lissum and his co-workers. And here you see a sensor node, very, very tiny, 70 millimeters in square. And here we have all together. We have power management. We have RFID for communication and energy harvesting. We have here this small microcontroller, 20 kilobytes of RAM, and analog digital converters, and a sensor, and so on. All together in very small size and very small volume. So, if we talk about virtualization on very low resource microcontrollers, we have to address efficiency. And host platforms and efficiency are belong together. Efficiency of data processing is always an important objective to optimize, especially for material integrated sensor networks. The efficiency of data processing systems can be compared by the following normalized performance factor epsilon. It's the product, or the quotient and the product, of the data processing system's computational power in instructions per second, MIPS, the memory capacity, RAM and ROM together in kilobytes, the entire chip area. Here you see a material integratable sensor node, and so the size of the computer is very important, and the electrical power consumption required to compute something. Of course, if you have RFID and harvesting the energy from an electromagnetic field, you are very limited in the choice and the selection of microcontrollers that are capable to be powered by RFID. So here you see a table with different microcontrollers, and here for instance the very well-known Atmel Tiny 20, here in this work addressed STM32 series, and of course the REXA VM is not only suited for software implementation, is suited for hardware implementations too, and here in comparison Xilinx Spartan FPGAs. And here you see different chip areas, different typical clock frequencies, and we assume one-to-one mapping or one-to-one scaling of a microprocessor. That means one instruction per hertz clock frequency. But the power consumption is very different, And so we get very different scaling factors or efficiency factors you see here. And we have totally different platforms here with only 8 kilobyte RAM. It's really the limit for the REXA VM, but we're typically addressing these devices here with 20 kilobyte of RAM or 48 kilobyte of RAM memory. So what's the concept? First of all, the VM, the virtual machine, integrates a compiler. We always bound the virtual machine, the execution system, with a text compiler. Programs and artificial neural network models too are always delivered in textual format. This is a very important concept. On-the-fly compilation to linear bytecode is provided by a very compact and efficient compiler requiring only or less than 600 lines of C code. No dynamic memory management except by stack operations is required. KISS keep it simple and safe. Less than 3,000 lines of C code for the entire virtual machine. Highly configurable with the custom instruction set architecture. And the VM can be directly embedded in I/O loops from microcontrollers cooperating with other tasks. Very important feature. So, here a short overview of the VM architecture, the memory model, the instruction set architecture that finally means the bytecode, real-time features and scheduling, the compiler itself, and of course you're waiting for the machine learning core operations. Here you see the architecture of the REXA VM, and it's a stack processor. That means most operations are performed via stack memories, data stack, return stack, functional stack memory, and some registers. And here we have the main VM loop executing bytecode instructions directly coupled, here you see it, to the compiler, the bytecode compiler. And one important feature of the REXA VM is there is no heap. There is only a code segment embedding data to and the stacks. That's all. Yeah. One most or very important feature of REXA VM is the input-output system interface, providing access of host platform functions and data to the VM instruction set. So the instruction set architecture consists mostly of operations with zero operand instructions, single word instructions operating directly on stacks or the program counter. With some exceptions, these can be freely defined. Zero operand operations consume only 1 byte, and most instructions have constant and equal execution times. That means we have some kind of real-time capability and a predictable runtime. The either is freely configurable, but the widely used and well-known fourth programming language will be used commonly, or any subset. There is no real standard. Here you see some highlights of the well-known fourth programming languages originating in the 60s of the last century and millennium. It's a reverse Polish notation, it's a stack language, and of course it's had the issue write once and forget, read never, but keeps compiler simple with low resource requirements and low compilation times. So here's the bytecode format, and it consists either of 1 byte, 2 bytes, or 4 bytes, or in between 3 bytes. It depends. Most instructions consume only 1 byte. Literals, short literals, only 2 bytes. Long literals, 3 bytes or 4 bytes. And finally, with a rest, for example, a jump instruction, we have a 3 byte instruction format. So, real-time scheduling is a very important feature of embedded systems and software embedded systems. And a sensor node, for example, in particular, has to process a set of tasks characterized by different priorities, arrival times, deadline, execution times. That means signal sampling, generation, event detection, communication, computation, energy management, service request and processing, and finally, watchdog services. And the REXA VM provides all the features that is required to process this virtual machine environment in a real-time, at least soft real-time context. So, and I can classify these tasks as event-based, data-driven, and communication-based tasks. So, and the execution loop of the REXA VM plays an important role You see it here. I highlight this. Here you see the execution loop, and the main loop of a microcontroller has to service, for example, analog digital conversions, digital analog conversions. It has to service communication via RFID, USB, or whatever. And then we have embedded the virtual machine execution loop and the compiler itself. And both can be executed incrementally. That means I can provide an upper bound of steps both for the execution of bytecode and the compilation of bytecode. And so I have an upper bound of execution time. And this is a very important feature we have here in this REXA VM, providing more or less constant execution time. The main VM loop is basically a monolithic switch case block, but optimized to a linear go-to-lookup table with constant execution time. Another very interesting feature is the system call gate interface, not really required for very, very low resource and small, tiny devices, but it's a very interesting approach to separate the VM itself from the host application. And there are two implementations. The most important is the shared memory interface, providing a communication between the host application and the virtual machine and vice versa. One example is shown here, a digital oscilloscope, and consisting of two application programs. The application program servicing the oscilloscope, analog digital conversion, digital analog conversion, and so on, and the REXA VM itself. And both can communicate vice versa via the system call gate interface. So a very important feature, additional feature for wide deployment of the REXA VM. Yeah, the compiler, only some short highlights. It's a just-in-time and incremental compiler. In-place compilation from program text to bytecode is always performed via the code segment. So the code segment is a very multi-purpose memory. Low memory requirements, usage of hash and index lookup tables for core instruction codes and user-defined data and code. And finally, only static tables used with constant memory requirement. Yeah, now coming to the main interesting part here, the machine learning part of the REXA VM. The REXA VM itself is not strictly correlated to machine learning, but it provides vector operations commonly used in artificial neural networks and convolutional neural networks. We are assuming only integer arithmetic. It's the only arithmetic you get in, or you can expect in, low resource and low power microcontrollers. And each INN and CNN can be decomposed in data parts and functional parts and structural parts. And both are provided by an REXA VM program. The model data, like the parameters, the weights, for example, of a neuron, and the code that is performing the computation of the artificial neural network or the convolutional neural network. And the basic idea is that each ANN and CNN can be decomposed in a basically chain of function applications. And this means we transform a neural network, for example, an artificial neural network, in a sequence of vector operations. And these vector operations using vectors, and that can be initialized arrays, for example, model parameters, or initialized arrays, like input, intermediate, and output data. So, and more important feature is vector array data is embedded in the code segment. There is a no heap. That means the program provides all the data and is compiled in place by the compiler in a code segment fragment. Yeah, here you see an overview of the vector operations. And for ANN and CNN models, a set of scaled vector operations is provided, commonly with 16-bit signed integer accuracy or resolution, data width. Most vector operations are using double precision arithmetics internally, for example, 32 bits. This is provided. ARM Cortex is a 30-bit 32 bits microcontroller, so it provides 32 bits arithmetics, and we are using this internally, but yeah, on the hood, on the front side, we are using the 16-bit arithmetics. So we have a lot of operations, the array operation itself, introducing or allocating space for initialized and non-initialized data. We have vector addition and multiplication, element-wise operations, vector scaling operations, folding operations used to compute an entire artificial neural network layer with multiple neurons. The convolutional operation and pooling operation, vecconv, a mapping operation, for example, applying the sigmoid operation, the sigmoid function used in artificial neural networks or CNNs. A reduce or reduction operation, for example, performing a sum and product operation on vectors. Yeah, and all these operations are used to compute artificial neural networks. Here you see an example, and this is all you need. This is all you need to specify an artificial neural network in REXA VM in the fourth programming language, or modified fourth programming language. Here we have the data part. It's one program, of course, but this is the data part with all the arrays. Here we have initialized parameter arrays like weights, biases, scaling factors, and so on, and non-initialized data like the input, the activations of each layer, and so on. And here we have the forward computation function that processes input data and applies the artificial neural network that here is composed of 14 input neurons, 8 hidden neurons, and 2 output neurons. In total, 24 neurons. And here you see the different vector operations. And finally, we get the output. Altogether, we are using a software development kit. So the code is not hard-coded static code. It's provided basically by code templates and code snippets. So the VM can be highly very highly configurable, and we can configure it or customize it for a specific application. There are not only software implementation, there are hardware implementation and simulation models too that can be provided. Here in this talk I concentrate only and I address only the software part. Yeah, and you can download it and try it here on GitHub. Here on GitHub you find the REXA VM source code and the compilation scripts, and you can try it on your generic computer on your laptop. And so using this software development kit with some scripts and compilers, mainly the code is stored in a JSON-like database, and then the final code that is compiled by, for example, the GNU-C compiler can be created by some scripts using the predefined database. Yeah, and one important point, I jump over it, but one important point that is addressed by the REXA VM is resilience. And this is addressed by a lot of concepts. First of all, by the KISS concept of the VM architecture, enhanced error detection and error recovery due to virtualization, isolation of critical architecture components. The pure textual code input is a very important point for resilience. Strict separation of control and data stacks. Tasks can only access private data directly. And for example, we can provide an ensemble VM execution, hardware or multi-core software implementation, executing the same code in parallel on multiple VM instances and comparing intermediate states and results, and providing, for example, a majority decision making. So there are a lot of more concepts provided by the REXA VM. Checkpointing, exception handling, adaptivity, hardware-software co-simulation, optional special data codings, and so on, that are inherent features of the REXA VM. But at the end, we have to talk about performance. And here are some highlights of the performance. And performance means here both the compilation speed, that means the mega compilations or compilation words per second, and the bytecode execution itself, of course, the mega words per second. And here you see typical results. Here we have the STM32 series, and you get around 1 MIPS, of course, word instructions, not native code instructions, on an ARM architecture, and you get about 15,000 word instructions per megahertz clock frequency. On an Intel processor, they are performing much more better. This is a well-known fact that our ARM processors underperform compared with Intel processors. And here you get about 90,000 instructions per megahertz. The memory requirements are very low. You see the lowest is 8 kilobyte for the code and 8 kilobyte for the data used by the virtual machine itself. Yeah, with different configurations, you see you can configure the code segment size, the data segment size, and so on and so on. Yeah, here's some highlights. We have a friction of about 1 to 70. That means about 70 native machine instructions per VM instruction is required on an ARM Cortex, or 1 to 15 on Intel architecture, x86 architecture. We have a friction of about 1 to 700. That means we need 700 native machine code instructions for 1 word compilation on the ARM Cortex and 1 to 100 on the Intel architecture. And we need about 30 nanojoule per VM instruction on an ARM Cortex, or 130 nanojoule per word compilation. Yeah, and computation time of medium-sized RNNs is below 1 second. I will show some charts at the end on an ARM Cortex architecture with respect to 60 megahertz clock frequency, and typically in the milliseconds range. Compilation times of medium and sized programs is below 1 second, typically in the milliseconds range, and the startup time is very low, below 100 microseconds, typically only a few milliseconds or below. Here you see the normalized computation time for different artificial neural networks. Here the ARM architecture, and here the Intel x86 architecture, of course with the gap 1 to 7 about. And here you see the scale is microseconds per 1 forward computation per megahertz clock frequency. And you see here it's more or less a linear scaling with respect to the number of neurons. And here you see the required code size, and it's really low. Yeah? Even for medium-sized artificial neural networks with about 40-50 neurons, you need less than 1,500 bytes for code and data, both. Yeah? So it's a very compact model. Okay, summary. A stack-based virtual machine architecture for low-resource, tiny embedded systems was introduced and analyzed. The overhead, even on very low resource systems, is low with respect to typical running times under energy constraints and tasks to be performed in real time. A major feature is the tight coupling of a text-to-bytecode compiler with the bytecode interpreter, ensuring robustness, security, stability, and interoperability in strong heterogeneous environments. Yeah, and finally, ML classification, machine learning classification, and regression models can be computed using integer arithmetic and a set of vector operations with low computation times and memory requirements. Yeah, thank you for your attention, and any comments and questions are welcome.